And it's been a while. You had a lot of turkey, a lot of vacation, relaxing the brain, I hope. Had a good time. So we're going to refresh a little bit. Just go over some few problems. Finishing up some problems that I had on that practice worksheet when we ended. And we'll go over some of those practice problems just to give you some comfort, some confidence in solving these problems. So let's look at that first one. And you're welcome to work ahead and say, hey, I got that. And then if I do it slightly different, I might even mess up. Usually it's not on purpose, but I might mess up so you can catch me with any mistakes. Because I'm human and make mistakes. I try to practice, and after doing it 1,000 times, sometimes talking and doing the problem at the same time is a little more challenging. So, go ahead and put your name on that practice, and let's look at this very first one. Could you do this one without me helping you? See if you can figure out how would you approach solving this problem. I'm giving you a little clue right now already. Remember our little, let's write up some rules. Whenever we see log some base b of some number x equals y, automatically think to yourself, oh yeah, b to the y equals that thing in the middle. You can even write this down, have it in your notes. Whenever you see that, what that means is b to the y equals x. And when you see b to the y equals x, think to yourself, oh yeah, log base b of x will give me y. I'm asking for b to the what power gives me x. And another thing that I like to, what happened to my pencil just was working great. Whenever I see log of 100, and my pencil was working great, and then stopped. Whenever I see log of 100, I know, oh yeah, that's 10 to the power of 2. That's how many zeros are there. So log of 100 is 2. Reminded you, oh, log is base 10. Oh yeah, it's how many zeros are in the decimal number. So log base 10, without any base there, remember there's an invisible 10. All right, giving you time to think about that one. Again, I apply that rule that I just reminded myself of. Log base 3 of 5x equals 2. That means 3 to the second power equals 5x. So I automatically take my definition of logarithm and say, oh yeah, 3 squared equals 5x. Well, you should be able to do 3 squared. And on the back of your worksheet, I printed out a handy-dandy little powers table for you. I don't expect you to memorize this, but maybe it wouldn't be bad to be familiar with those numbers, at least out to the power of 3. Squares, you should know your squares up to 10. And if you don't, just go ahead and practice that. Practice with your challenge your friends, or just kind of review that. It'll be handy on some problems. You recognize the power of a number. But if we don't have to have that memorized, because we have our calculators to help us out. But that's a good thing to keep in mind. You'll recognize, hey, that's an easy problem. I recognize that power. And so we know that 3 squared is 9. And then to isolate x to solve for x, we divide both sides by 5. And the 5 divided by 5 is 1, so we get x equals 9/5. And that was because we started, anytime we see a log problem, think to yourself, okay, I'm trying to solve for 5x in the middle there. Well, I know the definition of the logarithm is that little definition that I had there. All right, now how about this one? This brings in another law, and I can put that in my notes over here. When I have a log of a times b I know that that's the same as log of A plus log of B. Logarithms turn multiplication into addition, which is usually easier. But I've got a problem where I have this side. I have the addition side. And so the clue is, hey, if you have the addition side, how about going the other direction? When I see two logarithms added together, I also know that that's the same as log of x times x minus 6. And I set that to be equal to 4. And it's, I forgot the base. It is base 2. Remember, you can't add them together unless the bases are the same. Now I have one log on the left and a number on the right. And now I can go back to, I have it in this format, right? A log of base 2 of this thing is equal to this thing. Well, I can then go 2 to the 4th equals what's in the log. So I can say 2 to the 4th equals x times x minus 6. And now I can multiply it out. I get 2 to the 4th. Well, I think real hard. Well, 2 times 2 times 2 times 2, or 4 times 4, or 16. It's really good to recognize your powers of 2 in this computer age. Equals x squared minus 6x. Now what do I do? Well, let's subtract 16 from both sides, and that becomes x squared minus 6x minus 16 equals 0. And now I've turned it into a factoring problem. What values of x will make this equal to 0? If I don't recognize factoring, what can you do? X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. You could use your quadratic equation, but 4ac gets rather large. I could use my factoring. I see two numbers that when multiplied give me negative 16. When added together give me a negative 6. Well, let's see here. 16 is 1 times 16. 2 times 8. Ooh, 8 and 2 differ by 6. So I could do a minus 8 and a plus 2. And there's my factoring. X minus 8 times x plus 2 equals 0. And so I have the solutions. X is equal to either to 8 or negative 2. And I'll put it in smallest to largest. Am I done? Not with logarithms. Although I did the factoring, I have to come back and check. Can negative 2 be this x? Can I take a log of a negative number? And the answer is, sorry, negative 2 is not allowed. You don't get a x to any power giving you a negative number. So we can't use negative 2, but we can use 8. So our answer. Remember that when you factor, you still have to, although you have two possible answers that solve this equation, and remember how we got there? Well, we recognize the multiply rule, those logarithms added together, and of course, they better be the same base. And usually we're not giving you trick questions with different bases, but pay attention there. Sometimes you can't solve it if the bases are different. Making sense? Hoping to refresh. This is all refresh from last week. Well, the week before last. Now we have another one. Do you recognize the rule there? This is a slightly different rule this time. Well, we're going to find out. Right away when you see log x plus log 7, what does that turn into? Log of 7 plus log of x is the same as log of 7x. Yeah, we're multiplying. So we recognize log 7x. And now I have the log of two things, same base. The log of this equals the log of this. I don't have to worry about anything, but the things inside better be equal if the logs are equal. So I don't have to do any fancier things. I just say, oh yeah, x plus 6 better be equal to 7x if this equality is to be true. I can throw away the logs. So these are nice problems. If I see the log of something here equals the log of something here, that means the somethings are equal. So I can just say, throw away the logs, x plus 6 equals 7x. And it looks like a much easier problem. That's the whole point of the algebra, is rearranging things to make a harder problem into a simpler problem. Solve for x with all the little solving tricks that we have for puzzles. So what do I do here? Subtract x from both sides. So I get 6 equals 6x. And therefore x equals 1. I divide both sides by 6. 1 equals x. Well, let's see here. Log of x, log of 7 equals 1 plus log of 7. Oh, I know log of 1 is 0. So I get log of 7 equals log of 7. So therefore, 1 is the solution to that equality. I go back and just check my answer. So there's my answer, but it doesn't hurt to go back and check. You good with that? Okay. One more, still refreshing. And then one that over vacation I came across on TikTok. Sometimes I go there while I'm looking for fail videos that I love watching, or those number file videos, or videos about dark matter. That's one of my latest interests. But before I go to this one, let's look at this one. This looks a little tougher. What do we do? Well, one thing you do when you see an exponent, one of the easiest approaches is, how about I take the log of both sides? And I'll turn an exponent. Remember when we take a log of something to the x, or something to some power, that all goes in front of the logarithm. So I can do log of both sides. I don't know why my pencil mess up on me. Log of that. Log of that. Okay, so I get, I'll put log in front of that. Log of the 128. Let's put that in front of there. Something static or something messing up my pencil. Okay, so we got log of 8 to the 4x plus 1 equals log of 128. Remember the rule of logarithms. Whatever the exponent is, comes out to the front. So that becomes 4x plus 1, the quantity times log of 8 equals log of 128. Now at this point, I can now multiply out 4x log 8 plus log 8 equals log 128. Come on, equal sign. Log. I'm going to blame my recording software of 128. Come on, 8. There goes the 8. Now what can I do? Well, remember I want to get x by itself eventually. So what do? I subtract log 8 from both sides. I'm just doing regular algebra now. And now I can divide by log 8. Oh man, there's a lot of logs in there. But remember, my calculator can do all this calculation for me. So I get 4x equals log 128 minus log of 8 divided by log of 8. And since there's a 4 there, well, you know what? I can divide by 4 log of 8, and I have solved for x. Turn that into a 1. Now I have x equals all of this. And I can let my calculator do the work there. And I'm done. That's kind of a pain to do all that in the calculator. Is there a possible trick or one thing I could do to make this a little easier? Log right now is log base 10. But you know, this works for any base. And if you recognize 128 and 8 are powers of 2. So I don't have to use log 10. I don't have to use natural logarithm. I can use log base 2 and it's still true. That's another cool thing about logarithms is I can choose what base. As long as I use the same base in all of them, I can solve the equation. So I can choose to use, I either could feed this to my calculator and you get the right answer. Or I can also recognize, you know what, I could do this base 2 log. And I know that that's going to be log of 128. Oh man, what's base 2? Let's see, let's look at my table. Unless I have it memorized. It should be about 8 perhaps? Oh, it's 2, or it's 7. 2 to the 7th is 128. Okay, so I can just say, hey, let's do log base 2, and I can make that 128 is, log base 2 is 7. Log base 2 of 8 is 3. I know 2 to the 3rd power is 3. If I apply log base 2 of everything, so I'll make that log base 2. And that's 4 log base 2 of 8, or 4 times 3. Or 7/4. Now I would have gotten the same answer if I had just fed all of this into my calculator and used log base 10. So sometimes, and it's very rarely that all your numbers are going to be some power of another base. This was just one that I kind of worked up to let you see that if you recognize they're all a power of some base, you can use that base logarithm and maybe make the problem easier to solve, or it could be another check. I should get the same answer with either log base 10 or log base 2. Because the rules of logarithms apply, and I've used the rules all the way through, and they apply no matter what base I use, which is kind of a cool thing to remember. Yeah? Oh, I messed up. That's a 7 minus 3, not a times 3. I made my dash too long. Sorry about that. That's 4/4. It's even a simpler answer. Is equal to 1. Sorry. I was doing a 7 times 3 in my brain because I didn't make my minus sign large enough. Yeah, 7 minus 3 over 4 times 3. So that's not 4. That's 4 over 12 equals 1. There we go. There. Now I messed up on the bottom. 7 minus 3 over 4 times 3. That becomes 4 over 12. Or reduced to 1/3. Thanks for catching that. I accidentally turned a subtraction into multiply and it messed me up. Had to back up and correct that. So, showing your work would catch me. Oh yeah, that's where I messed up right there. Does that make sense? Use a different base, and if you recognize, hey, these are all powers of 2, again, a good reason to be familiar with those power tables. If I recognize powers of 2 everywhere, I can think, hey, let's try log base 2. Might make it easier. But you don't have to. You could use log base 10 and do this equation right here, and you're just feed that into your calculator, and you're good. Now here's one I got kind of excited. I was watching those fail videos, and here popped up a demonstration. They thought it was pretty cool. And I thought, you know what? This really isn't that hard of a problem for my algebra students. But for your average person that has forgotten all their algebra, it's not going to be as clear. So let's take a look at that. Pi to the 1 minus 2x equals e to the 2x. Whenever you see an exponential equation, think, let's just apply logarithm to that. Now, when I see an e in there, think to yourself, natural log will probably work better, because e is a friend of natural logarithms. So let's take the natural log of both sides and see what we get. If I do the natural log, and I'm going to write it out in cursive so I make it clear that it's natural logarithm of pi to the power 1 minus 2x. Remember, that's the quantity 1 minus 2x is equal to the natural logarithm of e to the 2x. Well, remember the rule. If I see log base e of some number x equals y, well, that means e to the y equals x. Natural logarithm e to the 2x is the same as 2x. Natural logarithm e to any, because remember, the natural logarithm of e is 1, so 2x, so that's equal to 2x. Waiting for my pencil to catch up to me here. And I'm taking a logarithm of something to a power. What do? I can put that power in the front. So that becomes 1 minus 2x, the quantity, times the natural logarithm pi, equals 2x. It still looks a little bit scary, but let's just do a little algebra with it now. We have natural logarithm of pi minus 2x natural logarithm of pi equals 2x. How do I get x isolated so I can solve for x? Well, the rule is get all the x parts on the one side. So let's add the 2x to both sides, and I get natural logarithm of pi I think my finger is messing up. If I cause the page to shift, then my recorder messes up the pencil. Let's see if I can keep that from happening. Natural logarithm of pi equals 2x plus 2x natural logarithm of pi. Do you see now this is 2x times 1 plus natural logarithm of pi? And guess what I can do? I can divide by 1 plus natural logarithm of pi, because that's something my calculator can figure out. So I get ln of pi divided by 1 plus natural logarithm of pi equals 2x. Only one more thing left to do to solve for x. Divide both sides by 2, and I get natural logarithm of pi divided by 2 times 1 plus natural of pi. See if the pencil catches up there. Come on, pencil. Thinking. And they made a big deal about this on TikTok because that's a really hard answer. Like a really genius solved that problem. And it's like, oh, dividing both sides by 2, I get this for x. Now that was just a little practice showing you that when I have what looks like a scary problem, applying logarithms to it, I chose natural log because I know natural log of e is 1. So that gave me a simplified thing on the right, natural log of e to the 2x. So natural log is what I aim for. But then this still had natural logs. But I used my rules of exponents. And then the rest was algebra rules to finally simplify for x. And this I can feed to my calculator. Now we're getting into the topic for today, which is more exponential equations, just different forms and ways to solve them. And this is one practice at it that I think you'll find not too bad. With this particular one, the thing to recognize is that 49 is 7 squared. And when I see that 49, I recognize that 49 is equal to 7 squared, I have two things. I have a 7, or I have two things, x minus 1 and a 2. It's the same base. I'm taking the same number to that power, like power. They call this the rule of the like powers. 7 to some power equals 7 to some other power. Well, in order for that to be true, well, then x minus 1 must equal to 2. The rule here is if I have a to some power x equals b, or equals a to some power y, the only way for that to be true is x must equal y. That's horrible writing pencil. Let's give it a different letter. Let's try, let's say b to some power x equals b to some power y. That can only be true if x were equal to y. Does that make sense to you? Something to some power must be equal to that something to some other power. That can only be true if those two powers are the same. And that's the rule of exponents. And if I didn't recognize that rule of exponents, what could I do? I could apply logarithms on both sides. I could say, well, I remember logarithms. Whenever I see an exponential equation, I could say log of 7 to the x minus 1 equals 49, or log 49. I could say, okay, x minus 1 log 7 equals log 49. I rest my hand over here. You'll keep that from happening. And now that becomes algebra. I could say x log 7 it was working so well before. Maybe it's something happened. X log 7 minus log 7 equals log 49. Well, then I have x equals, add log 7 to both sides, log 49 plus log 7, divide by log 7 after that would also give me the right answer, but it's a lot more work. If I recognize that 7, or that 49 is a power of 7, then I can use the simpler rule of, oh, x minus 1 equals 2. A lot simpler problem there, right? I recognize, oh, 7 to x minus 1 equals 7 squared, solve for x, x equals 3. So recognizing sum to some power is that same number to some other power lets me use the equal exponents rule. If I don't recognize that, I could still solve it by taking the logs of both sides and using algebra, and I have lots of logs in here. But notice these are. If I do all this work and then I realize, hey, wait a minute, these are all powers of 7. I could do log base 7 of everything. If I do log base 7, that becomes 2 plus 1 over 1. Because log base 7 of 7 is 1, and I get the answer 3. So I could always come back and say, wait a minute, powers of 7, let's do log base 7. That's always allowed because these rules of logarithms apply regardless of what base you're using. So I waited, checked your answer, and I got 3 there, but it was a lot less work when I recognize the power there. So having shown that, can you figure out this last one? And the clue is in your table on the back. Do you recognize 625 as being anything special? Look here. Oh, look. 625 is 5 to the 4th power. I didn't have to have that memorized, but you could say, hey, 625, I know it's a power of 5. I divide by 5, I get 125. I divide by 5 again, I get 25. Oh, 625 is 5 to the 4th. So you could do it a little bit step by step and divide by 5 a few times and realize this is equal to 5 to the 4th. Either by a table or by dividing by 5, getting down to smaller numbers, you realize, oh yeah, that's all divisible by 5 4 times. And then I can say 5 to the 3x equals 5 to the 4th. And when I see 5 to the 4th equals 5 to the 3x, what do I know? Well, same number to the same power better mean those two powers are equal. Then I know that 3x is equal to 4. Same number to 3x equals the same number to the power of 4. That can only be true if 3x equals 4. Solve for x by dividing both sides by 3. And I get x equals 4/3. All just to solve little puzzles along the way. Could you do that on your own? We've done the problems I've prepared for you. As we go through the textbook now, maybe we'll come up with just a few more practice to give you practice on your own. Any questions about that? This is the kind of whole thing. A lot of the algebra is recognizing the forms of the problem. And usually we help you by kind of giving you the form that we've just talked about in the chapter. So the form of the problem, when you see it this way, think to yourself, oh yeah, use the rule of logarithms and apply that puzzle. So you've got a toolbox of the problem in various forms. When you're adding logarithms, think to yourself, oh, let's try multiplying those things together and see what I get. And I get something that's a little more like the form of the basic logarithm problem. I turn this into a basic logarithm problem, and I see, oh yeah, that's 2 to the 4th equals that thing. And now it's simplified. I can solve for x using either factoring or quadratic equation. Same thing here. 7x I recognize because I'm adding logarithms. And then I get x plus 6 equals 7x. Turning a scary looking problem into a simpler one, that's the whole point of logarithms. They do that for the scientists. Back in the day when they didn't have calculators, people would spend, I don't know how, they were paid just to manually calculate tables of logarithms, and they had huge books. That was their calculator. Here's the logarithm for this specific number. They'd look up in that book that the master mathematician had written and made 1,000 copies of. People paid just to copy the book. That was their calculator. And so logarithms made those problems a lot easier. You have your calculators now that do that for you instead of looking it up in a huge book. Can you imagine those people having those problems and traveling to the library to find that book that had that particular algorithm that some person 100 years before had meticulously calculated out by hand? And that's where the logarithms came in, and they've still been useful solving what's a harder problem, turning it into a simpler algebraic problem. And that's what the mathematicians do. They simplified the life because they wanted to solve harder problems. So they make harder problems into simpler ones. So let's look then at our text for today that's basically going over what we just did in practice. So reviewing that, and let me find that document, our textbook for today. Where did it go? Here it is. So I got those multiplying rabbits. And just like what we just did, we use like bases to solve exponential equations. My wife was actually watching a documentary. Somewhere in the world, there was a place that they were short of rabbits. And they were breeding rabbits just to get them to repopulate. It must have been some very special kind of rabbits, because I didn't think we had a problem with rabbit population. But maybe this particular kind of rabbits. I don't think Australia had a rabbit problem. I think they were actually introduced. Some animal was introduced to Australia and that just took over the country. I don't know if it was the rabbits or something else. That just there was no natural predators, and it just rabbits come to mind, but I'm not sure. But that can happen in many places because populations grow exponentially. Remember that exponential problem is if the next year you increase by a certain percent, that's an exponential problem. Goes with diseases. If every week 10% of people catch a disease, it's going to grow exponentially. Now you have to keep in mind they also get over it and become immune, and though there's other pieces in the equation. But things that are fairly straightforward, an animal with no predators going to increase 10% each year, that animal is going to take over the entire continent very quickly, unless some other things happen, like they starve because they've eaten all the food, they've eaten all the trees. The locusts, every 17 years, they huge population, but they eat their food and then they die off because they've eaten their food supply. But that's another part of the equation. If you just look at population increasing at 10%, going to increase pretty nicely. And the important thing for you in your future job, that 401k increases at an exponential rate every year. That can grow very large, so when you're ready to retire, you can have a nice house and not live in a tiny little thing, although that's an okay way to live if you're happy. Okay, back to the like bases to solve exponential equations. Yeah, it was the rabbits, the Australian Mr. Thomas Austin. Thank you very much, Thomas Austin. 24 rabbits, just because he liked hunting rabbits, and uncontrolled population growth took over Australia. Various things regarding like bases. When we have some problems, such as this, 3 to some power equals 3 to some power divided by 3. Well, I just put that in the form of like bases, such as this. Let's take a look at it. Let's walk through this very carefully. I see this problem, Here, I'll go ahead and turn on my pencil here. I see that problem. Three to the 4x minus 7 equals this. Well, I don't see it 3 to some power because I want some base to something here equals that base to something else. I want it in that form. Well, in order to get that in this form, I have to recognize 3 to the 2x over 3 is equal to 3 to the 2x minus 1. This is the part that may be the challenging part to recognize. 3 to the 2x divided by 3. Remember, I'm subtracting 1 power of 3. Well, I can't just divide out the 3 and cancel it. I have to do a subtract 1 from the power up here. Think to yourself, when I see this, say if I had 3 squared over 3, I know that's equal to 3 to the first power because 3 squared is 3 times 3 over 3. That cancels out 1, 3. But when I don't know what the x is, I can only turn that into 2x minus 1. So here is the goal. When we have the like bases, 3 to some power equals the 3 on the other side to some power, now is when I can take these two things in the powers and set them to be equal to each other. The same base to a power is equal to that same base to this other power. That lets me then go to this step. When I have two things to the two different powers that are set to be equal, I know those two things then are equal. And then it becomes an algebra problem. So subtract 2x from both sides, gives me 2x. Add 7 to both sides, gives me the 6. And then we divide by 2, gives me x equals 3. So the main part of the problem is getting it into this form. Remember, with solving a problem, we want to get it into this form of the problem. If I have it in that form, then I can set the x equal to y. I know that's the rule of the 1-to-1 power. And they state it here just with different letters. If I have s and t as my exponents, and I have some number to that power, that is my rule. That's what we call the 1-to-1 property of exponents. So they restate it here is we want to get the equation into that form. If we can get it into that form, then I can use the 1-to-1 property. So another rule, when you see exponents, you could do log of both sides, and you'll get the right answer. Or recognize that I have 2 to that power. I could prove this using log base 2 as well. But let's not worry about that. Let's just memorize the 1-to-1 property. You don't have to go through proofs of things. We just know that when I have 2 to this equals 2 to this, that must be these two things inside must be equal. So I know right away, I didn't even have to do any manipulation. I could say x minus 1 is equal to 2x minus 4. Let's do it carefully. First of all, let's subtract x from both sides. So we get negative 1 equals x minus 4. Subtracting x from both sides. Now let's add 4 to both sides so I can get this negative 4 out of the way. So that becomes adding 4 to both sides, 3 equals x. So we'll do it. Add 4 to both sides. This was add x to both sides, or subtract x from both sides. Now suppose you were given the problem 2 to the x divided by 2. Do you recognize that that's the same as 2 to the x minus 1? It's the same as 2 to the 2x divided by 2 to the 4th. So sometimes just to give you a little bit of work to get it into this form, they might give you the problem. But recognize whenever there's a negative power, that's the same as that number being underneath. So if you're given a problem like this, think to yourself, hey, wait a minute. I can do a -4 up here, and I can do a -1 up here, and I put it in the form of the base to some power. Same base to different powers. So we'll be giving you problems like this to give you one more step to put it in this form. So the goal is when you're in this section, you'll be given problems, and your goal is to somehow get it into the form of that 1-to-1 equation. B to the S equals B to the T. You want to somehow get into that form through some manipulation. You can get into this form by rearranging things. Then you have turned it into a this exponent equals this exponent. And they're not going to make it a lot harder, but let's take another practice question here just to practice our skills here. Again, they gave us the problem in the same base form. Now my computer's slow. When I record, at least if I'm running Teams and recording, I have actually crashed my computer. Don't know why. See this problem? Same base. I'm good for equating the exponents. So I can right away jump to 2x equals 3x plus 2. I don't know if there's a solution. I just know I can go from here to this equality. Now remember, well, let's see, what else could I do? That's the same as 5 squared times 5 to the 3x. I recognize this as 5 squared times 5 to the x. No, that's 5 to the 2x. Maybe there's a way to get a 5 out of there, but I don't need to do that. I can just set the exponents equal, subtract 2x from both sides, because I want to get 3x by itself, so I get 0 equals x plus 2. Subtract 2 from both sides, and I get -2 equals x. Check my answer. 5 to the -4th equals 5 to the -6 plus 2, or 5 to the -4. So that's why they say, to get things into that form, we need to find the similar base. And one of the favorite bases is base 2. We can somehow get the same base. Here they show you using base 2. But I also know that 256 is 4 to the 4th. If I look on my table, yeah. We'll look at their way, and then we'll also show that we could have used base 4 and solved it quicker. They say, well, I recognize base 2's here. See how they did. 4 is base 2. Remember, we have to then multiply out. When I do 2 squared to the x minus 5, that becomes 2 to the 2x minus 10. You got to be super careful when you're multiplying. When you're taking a power to another power, remember they multiply. So be super careful when you go from there to there. It's easy to mess up that step. You make sure when you see 2 squared to the x minus 5, remember it's 2 times the quantity x minus 5 to get your full exponent. If we recognize 256 is 2 to the 8th, well, then I just do 2 to the 8th. See how then this becomes same base. Now I can set the exponents to equal, and now it's just a matter of solving for x. Let's see, we add 10 to both sides, we get 18 with 2x. Divide both sides by 2, and I get x equals 9. Now suppose I recognize that this is 4 to the 4th. Well, look how simpler my problem can be. I recognize that as 4 to the 4th equals 4 to the x minus 5. Recognize my powers of 4, and look how much simpler the problem is. 4 equals x minus 5. Well, the only solution for x is adding 5 to both sides. I get 9 equals x. Look how much quicker I got to the answer by recognizing 256 is a power of 4. They showed you recognizing base 2. Would have got the same answer, but a little bit more work. So again, if you see powers of things, that's why it's good to have that power table handy, and you can have that available to you when you're working on the test. You may see recognize a power. Remember, all we did was look for a way to get it into the form. This is the key right here. Once I get into that form, b to the s equals b to the t, then I apply my one-to-one rule. I can't apply the one-to-one rule until I get to this step. So you see this, you're not quite at the one-to-one rule. You got to multiply that out. Make sure that and if it helps, I often will do this. I will often put this in parentheses just to remind myself it's 2 to all of that. It's easy to forget that that's not 2 to the 2x minus 2 to the 10th. It's 2 to the quantity 2x minus 10. So put parentheses around this to remind yourself whenever you see that, just so you don't accidentally separate those out and get the wrong answer. Let's see here. We got time. We'll come back to this. Let's go to the Lumen homework that you're going to have online for you. It's due Friday. I'm going to help you walk through a few of those problems. They have some real easy ones. But let's take a few of those, and I'll give you hints, and maybe help you give the answer for a couple of them. Remember those Lumen problems, it's for you to see if you can basically give you more practice and give you credit for it. Now the first one, let's see, I'll zoom in a little bit here. The first one should be pretty straightforward. Now let's make sure that you're comfortable with how you get this answer for this first one. Same base, two numbers, the same base equal to something. Another pencil. Pencil, come on, turn on. There we go. What do you see as the answer? 7 to some power equals 7 to some other power. B to the S equals B to the T. What is x equal to? Here's my one-to-one rule. You see the one-to-one rule applied here? And don't be embarrassed if you don't. This is the time to see, wait, there's an x on this side. There's a negative 6 on this side. It's like, wait a minute, is it that easy? Yep, they like to start out with real easy ones. The only way for this to be true is for x to be equal to negative 6. That must be equal to that. Same base. That's my S, and that's my T. So those things must be equal. So x must be equal to negative 6. That's the only way that this could be true. X has to be negative 6 in order for 7 to the x equals 7 to the negative 6. Now they do get harder, but that's the basic 1-to-1 rule. They're being nice to you, starting with an easy one. I recognize my base as 7. Now they do get a little harder. This one, we got to do a little algebra first to get it into some form, and we're hoping that they've given us some clues here. Let's just do the basic thing here. The first thing you would do when you see a problem like this, first thing you do is we want to get rid of this on this side. We want this to be 5 to the 5x, 5 times 5 to the x equals some number. So we want to add 38 to both sides right away. So adding 38 to both sides gives me 625. So we get 5 times 5 to the x power is equal to 625. Now they've given you a clue there. Hey, we can divide both sides by 5 because this ends with 5. So I know this is a multiple of 5. So I get 5 to the x. Dividing by 5 gives me 125. Now I can't apply any like basis rule unless I can recognize that this is some power of 5. And you recognize that that is 5 times 5 times 5. So that is 5 cubed. That's something that you just have to, well, you could divide it by 5 3 times. 125 by 5 gives you 25. Divide by 5 again gives you 5. Oh, so then you get 5 cubed. Or you could have it memorized from your little table. Now we have it in the form some base to some power equals that same base to some other power. So what is x? The only possible answer is x must be 3. Because the like base, the like power of the same base, I know that they're equal. If that equality is to be true, x must be equal to that power on that side. Pencil will just stop working and then work great for a while. Alright, next problem. Time to use the table. I don't remember all my powers of 3, but let's see. One way to know do you know the one rule about knowing if it's a power of 3 or it's a multiple of 3? That if the digits added together give you a multiple of 3, then it is a multiple of 3. So 2 plus 4 gives me 6 plus 3 gives me 9. I know that 243 is a multiple of 3. So I could keep dividing out by 3 each time. Or I could go to my table and see that 243 is 3 to the 5th power. I don't expect you to memorize your powers of 5. Powers of 3 would be good, but you should memorize the squares. But you could just keep dividing by 3. And you'll see that 243 is 3 to the 4th power. When I'm doing it, and I don't remember that that's power of 3, divide by 3 first. So 43 divided by, and I get, well, let's see, 80 times 3 is 240. So I get 81. Oh, I recognize that that's 9 squared. Equals 3 to the 4th. So 243. Oh, there's another 3. Multiply that by another 3, and I get 3 to the 5th. So times 3, So that one way to seeing, oh yeah, 243 is equal to 3 to the 5th. However you do it, dividing out multiple times by 3 until you see, oh yeah, that's another power of 3. So we put over here 3 to the 5th. Now I know x is equal to 5. Suppose I didn't remember my x's, my powers of 3. What would you do? You can always go back to what you know about logarithms, and you can just say log of 3x equals log of 243. Sorry, log of 3 to the x. And I know that x log 3 is equal to log 243. And so I have a calculator, I could say, okay, I'm just going to use logs to solve this. X equals log 243 over log 3. If I don't recognize 243 as a power of 3, I could solve it this way. Now, they are saying you use the like basis property. I'm not using the like basis property here, but I am finding the answer. If I recognize that this is a power of 3, well, then I can do log base 3 of 243 is equal to 5, and log base 3 of 3 is equal to 1. So recognizing, and so that you'll usually can tell from what power is over here. This is probably power of 3, unless they're really trying to make it harder for you. If it's not a power of 3, I can always go back to what I know about logarithms and solve my problem using logs. I don't think we're going to be giving you a trick problem like that. If it's not a power of 3, you can always go back. If they say use logarithms or power or like bases to solve this problem, you could just crank it right into, take natural log of both sides. Whenever you see an exponential problem, taking a log of both sides is one of the first things to consider, just like in that TikTok problem. But since we're working on like bases in this chapter, we're looking to put it in that form of like bases. But we still have our other tools that we could still solve the problem with. And that's another one of the reasons, the beauties of logarithms. They can solve problems that maybe could be solved another way, but I can still crank on it with logarithms and get the right answer. Because logarithms have this beautiful property of multiplying gets turned into addition. Powers get turned into multiplication. Simpler answer. So now they give us an exponential problem. First thing I would do here is probably divide everything by 6. And then I can take the natural log of both sides. Let's do that one for your last practice problem on your notes. Just do this one on your notes. See how far you can get with that. Could you solve that one on your own, getting the exact solution? They suggest using natural logarithms. See how far you can get on your own. And if you get stuck, I'll work through that. But pretend this is your exam. You have to do this problem. Could you solve this? I guarantee you're going to get a problem like this on the exam. So if you can practice doing it now, and I help you through it, you'll be that much better to be ready for the exam. And I hear some of you are getting to the ASC for help. Good job doing that. They are there to help you. They're really good people. All right. I'll first do the divide by 6. That's the thing that I right away go to. Get this by itself. Get the e by itself on one side. So we'll get e to the x plus 1 equals 11 over 6. And whenever you see e, remember, natural logarithms are probably something we want to use. Let's take the natural log of both sides. And the natural log of e to the x plus 1, I'll just do ln of all of that, equals the ln of this. Well, logarithm, natural log of e to any power is that thing. So we know that x plus 1 is equal to natural logarithm of 11/6. And now I can solve for x. I subtract 1 from both sides, and I get x equals natural logarithm of 11/6 minus 1. That is the exact answer. That's what would go here. Natural logarithm 11/6 minus 1. That's the exact solution. Plug this into my calculator, and I can find the exact solution. Let's go ahead and I'll fire up my calculator. I'll calculate 11/6, get the natural logarithm, and subtract 1. So calculator. It remembers, I think, that it was last in scientific notation. So I do 11 divided by 6. Get the natural logarithm. Where's my net? There it is right there. Natural logarithm. Oh, let's try that guy. Not sure that's right. Let's do 11 divided by 6 equals, there we go, natural logarithm. I have to do the equals before then taking the natural logarithm of that. Now subtracting 1 minus 1 equals minus 0.3939 because that last 3 rounds up. So for my calculator, just to make it easy on the calculator, I calculated 11 divided by 6, then ln to get the natural log of it, and then subtracted 1, and making sure my rounding 0.393, 8 rounds up to 9, 0.3939. Well, let's see here. Let's take another problem to look at. Do we see, can we do the 1-to-1 rule here? X, or 5 to the x equals 47. Nah, 47 is not a nice multiply of anything. It's not a multiple of 5. So, my only choice is to do log of both sides. And I'll just do the log part. I can even do log base 5 if I want, but that's not on my calculator, so I'll do log this time. I did natural log this time. I don't see any e's in here, but I could also do natural log. But let's just do log, since some calculators don't have natural log. They only have log. So let's take log of both sides. Log 5x, 5 to the x, put that x in the right place, equals 47, log of 47. 47. Let's rewrite that. Horrible writing. Log 5 to the x equals log of 47. That becomes x log 5, right? 5 to some power. Take the log of it. X log 5 equals log 47. Wait for my pencil to catch up. And I can solve for x. Come on, 7. Come back in there. There we go. Solve for x just by dividing by log 5. So I know the exact solution is log 47 divided by log 5. and feed that in my calculator, and I can get the calculate to decimal place. I think that's enough for our brains to work on so far. You have in your toolbox, using logarithms, see an exponential equality, apply log to both sides. You might want to, if you see logarithms added together, you do the, hey, that's the log of those two things multiplied together. Sometimes that you can do the equality then. If you have log of two things, you know that the inside the log are equal. Sometimes you have to do you see the equal exponents. You get the same base to some exponent on either side. That's the form of b to the s equals b to the t. Then solve, s equals t. Here, we can't do either one. There is no 5 to some power on both sides. So we go back to our, hey, take the logarithm of both sides. And you know what? It doesn't matter what base. I would have gotten the same answer if this were natural log 47 over natural log 5. Just so long as you're using that rule. If you apply the logarithm, use the same one on both sides. Don't use log on one side and natural log on the other. You get the wrong answer. I think that's enough for you today. Turn in your problem sheets. If you have any exams, I still have some exams. Exam number 3, version 1. If you want your copy, I have it here if you want to look through. Kylie, Valerie. I think those are your notes with it, right?
Yeah. Thank you.
Kaylin. Brady. Kaylee. Randy. Maddie. This is exam 3, version 1 if you wanted that. Maddie. Kiera. Cam. And Rose. You want to come grab your exam for that. And turn in your notes for today, and you can get them back. I use it for attendance and any comments. Love your comments. Something foggy. You need to make it more entertaining. Bring in the banjo. Sing the quadratic equation song more often. Maybe we could sing an exponential song. Have a wonderful day. Welcome back. Glad you're back. Glad you're healthy. We got some that are having some drama in the middle of the night. Thank you. Good job. Have a great day. Thank you. Oh, Hattie, did you want your exam back now?
I'm good. Thank you.
Okay. And I will stop the recording.